Welcome to the 26th lecture on computational mathematics with Sage Math. In this lecture, we will look at how to find maximum and minimum of function of two and more variables. So, let us first start with some definition. So, suppose you have a function f from R2 to R. It can also be defined on some subset of R2 to R or a function from Rn to R. Then a point P whose coordinates are a and b is called a global maximum if you take any point x y in the domain of f, then we have f of a b greater than equal to f of x y. Similarly, if P is called a global minimum if for any x y in the domain of the function we have f of a b less than equal to f of x y. However, this point P is called a local maximum if there exists an open ball B P R centered at P with radius r is same as saying there exists r positive and this ball B P R such that for any point x y inside this ball we have f at a b bigger than equal to f at x y. Similarly, you can define local minimum. For local minimum, again the same thing, but this condition should be f at a b less than equal to f of x y. But in case this point P is neither a local maximum nor a local minimum, then what is the condition that you are going to get? In that case, if you take any radius r, any r positive and take the ball B P R, take the open ball B P R, then you can find 2 points x1 and y1 and x2 and y2 such that at one point function value is less than f at a b and other point function value is bigger than f at a b. So, in that sense in any small neighborhood function will have smaller value and bigger value, that is what it means. Such a point generally we call as a saddle point. So, now before we look at how to find these local maximum, local minimum, first let us look at graph of a surface. So, this is a surface z is equal to f x y, and if you look at this graph, so for example this point and this point are point of local maximum, and so for example if you look at the gradient at this point, what will happen? What is the gradient? Gradient is the direction in which function increases with maximum speed. Now, since you are already at the point of maximum, there is no direction in which function is going to increase, therefore the gradient at this point will be 0. The gradient of the function f at this point is 0 is same as saying first order partial derivatives at this point will be 0. Similarly, this the case. Similarly, if you look at let us say this point, this is a point of local, this is a local minimum. So, at this point again the negative of the gradient will be 0. That is because this at this point if I look at the negative of the gradient, that is the direction in which function decreases with maximum speed, but at this point there is no direction in which function is going to decrease because it is already at local minimum, then the negative of the gradient will be 0 is same as saying gradient is 0, and again you have, that means the first order partial derivatives at this point will also be 0. Similarly, if you look at or you look at these 2 points, again point of local maximum or local minimum, at this point if you draw the tangent plane to this surface, that tangent plane will be parallel to xy plane. So, that again tells you that if the tangent plane is going to be parallel to xy plane is same as saying the tangent plane will have an equation z is equal to some constant, that again tells us that the first order partial derivative of the function at these points should be 0. Similarly, if you look at this point, if you look at this particular point or down below, okay, this is the only point in this case. At this point also if you try to draw the tangent plane, that will be parallel to xy plane. So, again at this point the gradient will be 0. However, at this point when you draw the tangent plane, no matter how small a portion you take of this graph, the tangent will intersect the surface, but that is not the case at the point of local maximum or local minimum, right. So, this point is called saddle point, and that is what you get here at any small portion of this the surface. The function value will be higher than this function value at this point, and it will also be lower. So, that is why it is called a saddle point. Okay. So, these are the some points, and in case you look at the contour plot of the same surface, this is how it looks like. So, in this case you can see that one of these 2 points, this point, this point, this point, this point, these points may be point of local maximum or local minimum, because the contours near local maximum will be some kind of concentric closed curves. It will be a kind of circle, closed concentric circles, and this is a saddle point where this contours will look like some kind of hyperbola, right, rectangular hyperbolas, right. So, these are the geometric meaning of local maximum, local minimum and saddle point. Now, let us look at how we can find these points. So, let us start with an example, but before we look at the example, whatever we saw geometrically, let us just write them, and then let us write the condition for local maximum or local minimum. So, first of all, all those points where this gradient is 0 are called critical points. So, local maximum and local minimum and saddle points are going to come from these critical points. Critical points are also known as stationary points. Okay. So, and at these points, in case the function has local maximum or local minimum at any point a b, then we saw that the gradient at that point must be 0, is same as saying first order partial derivative must be 0. So, that is the necessary condition for a point to be local maximum or local minimum or a saddle point. Okay. So, but then in order, once you have found the critical points, in order to find critical points, you have to solve gradient of f equal to 0 for all those value of a and b, and once you have found the critical points, then at these critical points you need to classify whether it is a point of local maximum or point of local minimum or a saddle point. And then this you have second derivative test, very similar to one variable case. In one variable case, you must have seen that in case x is a critical point, that is f dash x is equal to 0, then that x will be point of local maximum, provided the second order derivative at x is negative, and if the second derivative is positive, then that point is local minimum, right. That is what you have seen. So, here in this case second derivative of f is a matrix which is called Hessian of f at the point a b. So, this is what is the Hessian? Hessian is this matrix of second order partial derivatives. So, this is second order partial derivative of f with respect to x twice, this is f partial derivative of f with respect to x, then followed by y, and here this is partial derivative of f with respect to y followed by x, and this is second order partial derivative of y f with respect to y twice. But if you look at suppose we assume that the function is twice continuously differentiable, in that case this Hessian will be symmetric, because this mixed second order partial derivatives will be the same. That is what we saw. So, in that case all eigenvalues of h will be positive, and this Hessian is called positive definite if all its eigenvalues are positive, or this f x x at a b is positive and its determinant is also positive. Then we say that Hessian is positive definite, and it is negative definite if minus h is positive definite. So, that is same as saying f x x at a b should be negative and its determinant should be negative. Okay. So, this is definition of positive definite and negative definite, and in case h is positive definite at the critical point, that then that point critical point is a local minimum. Similarly, if the point a b the Hessian is negative definite, then that point is local maximum. So, again you can see here this is consistent with one variable local maximum and local minimum, and in case the determinant of this Hessian, that is f x x at a b into f y y at a b minus f x y whole square is negative, then such a point is called local is a saddle point. It is not a local maximum local minimum. So, that is a saddle point. Okay. Now, let us look at some example. So, first let us start with finding critical points and classifying them for this function f x y is equal to 4 x y into e to the power minus x square minus y square. So, first let us define x y z as variables, and f x y is equal to 4 x y into e to the power minus x square minus y square. And then in order to find critical points, first we need to solve gradient of f is equal to 0 is same as saying first order partial derivative of f with respect to x and y must be 0, right. So, and you can even plot graph of this function along with the contour, and what we saw these graphs of the surface and this contour are exactly graph of that function f of x y is equal to 4 x y into e to the power minus x square minus y square. So, you can see here this function has two local minimum, two local maximum and one saddle point. That is what we expect, and that again is confirmed by these contour plots. Okay. So, first let us find out the first and second order partial derivatives. So, this is first order partial derivative of f with respect to x, then followed by first order partial derivative of f with respect to y. So, that I am calling as f x f y. This is second order second order partial derivative of f with respect to x twice, and so on. So, let us evaluate this, and once you have evaluated this, let us find the critical points by solving f x at x y equal to 0, f y at x y equal to 0 for x y, and with the condition that you enable solution dictionary is equal to true. So, it will give you a solution in as a dictionary. So, let us run this. So, once you run this, it may take some time depending upon the function and the complexity of that function. So, okay. So, it has found as you can see, it has found 5 critical points. One is 0 0, other one is minus half square root 2, minus half square root 2, and so on. So, these are the 5 critical points. Now, these critical points we need to classify. So, if we want to classify these critical points, that means at these critical points we need to find the Hessian. So, let us just take one of the critical point. This is just we can run a loop over this solution, all the solutions, and try to print these critical points in a pretty print format. So, these are the 5 critical points 0 0 minus half square root 2, this is same as saying 1 by square root 2 minus 1 by square root 2 minus 1 by square root 2, this is square root 2 minus square root 2, and so on. Okay. Now, let us say suppose this we have already done. So, let us not get into this. Suppose we want to find or classify this third critical point here. The third critical point in this list is this one, square root 2 minus square root 2. So, suppose we call that as we call this in as a comma b as the third critical point, and just a second. So, the square bracket is missing, this should be inside this. Yeah. So, this is the third critical point. At this critical point, let us look at what is the Hessian. Now, so Hessian you can obtain in Sage Math just using f dot Hessian command. So, this is f dot Hessian will give you Hessian. So, that will be a function of x y. So, now you can evaluate this Hessian at a b. So, let me call that as h1. H1 is Hessian h at x comma x equal to a, y equal to b. So, that is the Hessian. So, it is 8 into e to the power minus 1 0 0 8 e to the power minus 1. So, e to the power minus 1 is positive, that means this Hessian is actually positive definite, because this term is positive and its determinant is also positive. Therefore, this point is a point of local minimum, right. So, we can also find whether this Hessian is positive definite or not by using inbuilt function. So, first we will change the entries, the domain from which these entries are taken. This RDF means this real field. So, let us change this entry, otherwise it may be a symbolic field. So, let us for example check h dot I do not know whether there is a function called ring. It should be h dot parent. Okay, h dot parent. So, it says that this is a full matrix 2 by 2 dense matrix over callable function and ring with arguments x and y. Let me call this as h1, right. So, this is a symbolic ring. So, this is a symbolic matrix in that sense. So, it will not be able to check whether it is local maximum positive definite or negative definite. That is why you change the ring, that is the entries from which it is taken. So, now if you look at what is h dot h1 dot parent, then now this will be a real double field, right. So, now you can use this command h1 dot is underscore positive definite. This will tell you whether it is positive definite or negative definite, right. So, and the value of the function at this point at this critical point a b is minus 2 into e to the power minus 1, that is a negative value. Okay. So, that is how you can check a given point, critical point, whether the Hessian is positive definite or negative definite. Okay. Now, let us look at, we can create a small user defined function to check whether a critical point is local maximum or local minimum. So, for that we are just defining this first or second order partial derivatives. This is the determinant of the Hessian, and first you check whether the first term, that is first order partial derivative of a with respect to x twice, is positive. Once it is positive, then check first you check the determinant. If the determinant is positive, then check the first term in the Hessian, that is f11, which is first order partial derivative of a with respect to x twice. If this is positive, then it is local minimum. If it is negative, then it is local maximum. If it is not positive and not negative, then the test is inconclusive. And in case the determinant is negative, this is a saddle point, and again if the determinant is 0, then again the test is inconclusive. When in case this test is inconclusive, one can go for higher order partial derivatives and then try to classify. Let me not get into those things, right. So, after you have done this define this user defined function to check whether a critical point is local maximum or local minimum, then we can call this function and try to tabulate each point, its nature and the function value. So, this is a small loop which what is it doing? It is creating a table of critical points, the type of the critical point and the value, and then first you are solving this in the dictionary, and then for each solution inside this dictionary, you have to check whether the solution is real or not, because if it is not real, then that is not a critical point, and then define A to be the x coordinate, b to be y coordinate, and then append that into the data. So, this is the data which we are creating, and then after that you print that data. So, I think I did not run this user defined function. Now, let me run this user defined function and see what is going to be the table, right. So, that is the table of classification of critical points. So, 0 0 is a saddle point, its function value is 0, this is a local maximum, the function value is this is local minimum, function value is this, and so on, right. So, this is how we can classify critical points in function of 2 variables, and you can extend this to function of 3 variables, except that this condition you need to now check on positive definiteness or of the Hessian, right. Okay. So, next let us look at one more example. So, this is the function f of x y is equal to 3x minus x cube minus 2y square plus y to the power 4. If you try to plot graph of this function, that is the surface, this is how it looks like. So, in this case you can see here there is one point of local maximum, there are 2 points below, this is a point of local minimum, and this is going to be a saddle point. This is one saddle point here, there are other saddle points inside this. Yeah, so this is another saddle point, this is another saddle point. So, it has 3 saddle points and 1 point of local maximum and 2 local minimum. Similarly, if you try to plot the contours, then that should confirm that it has 3 saddle points. So, one saddle point will be somewhere here, other saddle point is somewhere here, other saddle point is somewhere here, and these going to be point of local maximum or minimum. So, in this case we saw that this should be point of local minimum and this is point of local maximum. If you want, you can increase the contours. So, let us say contours equal to, let me make it 30, it may take more time. Contours equal to 30. Oh, twice I have written this contours. So, this instead of 20, let me make it 30, and then yeah. So, you can see here that you get more contours, right. Now, let us classify them. So, find all these first and second order partial derivatives, and then let us find the critical points by solving these gradient equal to 0. So, again you can see here this confirms that it has 5 critical points, 1 0 minus 1 0 1 1 minus 1 1 1 minus 1 minus 1 minus 1. Now, in order to classify this, we will again tabulate the critical point and its nature, that is whether local maximum, local minimum or saddle point, and the function value by just running this again this loop and calling this the extreme function, user defined function that we have created. Once we do that, and then let me create the table of this. So, you can see here this is 0 0 is 1 0 is local maximum, function value 2, this is saddle point, function value minus 2, this is 1 1 is again a saddle point, and for example, minus 1 is a local minimum. So, there are 2 local minimums and 1 local maximum and 3 saddle points. That is what we saw from the graph. So, you can do more examples. One of the another very standard problems that you may find, you can try to find out let us say relative or absolute maximum and absolute minimum. So, in that case, apart from finding this local maximum, local minimum in that given domain, you also need to evaluate the function along the boundary point and compare the value of the function with local maximum, local minimum. So, in case the function value which is the smallest among local maximum, local minimum and the function value at the boundary point will be absolute minimum, and similarly you can find absolute maximum. Okay. So, and it has several applications. So, we will look at its application in what is called least square problems in the next lecture. Let me leave you with a few exercises. These are straightforward exercises. So, this is a function whose critical points you need to classify. This is another function defined on this closed and bounded domain, and you need to find absolute spelling mistake, absolute maximum minimum. So, as I said, you need to first find local maximum, local minimum, and then also find the function value at the boundary point and then compare. And this is find the point on the plane that is nearest from the origin. So, that is same as saying if you take any point on this plane, look at the distance, you need to minimize the distance. So, distance from this any point x y will be square root of x square plus y square plus z square, but then square root is not a differentiable function. So, you need to find the or minimize the square of the distance function, that is x square plus y square plus z square, and this is what you need to minimize. So, that is a very easy problem, and this is again a problem in 3 variables. So, you need to find the partial derivative with respect to 3 variables, all these 3 variables x, y, z, find the critical points, and then check whether the Hessian is positive definite or negative definite in order to classify. Okay. So, thank you very much.